All right, let's jump right into today's explainer. We're unpacking the Phase 1 Week 2 Cybersecurity Study Guide, and man, it is absolutely packed with networking essentials. As I was going through this, it hit me. The real takeaway here is building a rock-solid mental model of how data actually moves. Because, whether you're trying to intercept credentials or defend a massive corporate network, you've got to know the terrain. Which brings us to this defining quote from the source material. Everything in cybersecurity travels through a network. The network is the battlefield. That really sets the stakes right away, doesn't it? Almost every single attack you'll ever encounter involves the network layer in some capacity. So the bottom line is this. You literally cannot exploit, and you definitely cannot defend, a system that you do not fundamentally understand. So here's our game plan for this explainer. First, we'll map out the OSI model. Then we look at transport, addresses, and ports. Third, we'll decode core infrastructure like DNS and DHCP. Fourth, we'll hit the active war zone of subnets, firewalls, and attacks. And finally, we'll cap it off with the ultimate interview question. By the end of this, you're going to have a mental map to crush your next technical networking interview. All right, Section 1, the OSI model map. Let's start mapping the terrain of our network battlefield using these 7 abstract layers. Okay, before we get bogged down in the heavy technical jargon, the guide shares this absolute classic memory trick. Please do not throw sausage pizza away. Look, I know it sounds totally ridiculous, but it works flawlessly to lock in the order from the bottom up. Physical, data link, network, transport, session, presentation, and application. Seriously, burn this into your memory. Now, what's really fascinating here is how every single layer has its own unique attack surface. Down at layer 1, the physical layer, you're dealing with actual cables and Wi-Fi. So the attacks are, well, physical. Think cable tapping or jamming. But as you climb all the way up to layer 7, the application layer, you're looking at HTTP and DNS. That opens the door to stuff like DNS poisoning and HTTP floods. Whenever you stumble onto a new vulnerability or fire up a new hacking tool, you've got to ask yourself, wait, which specific OSI layer is this operating on? It's a real game changer for sharpening your tactical thinking. Here's the core cheat sheet straight from the study guide, mapping out this foundational terrain perfectly. Attackers and defenders reference these layers constantly, like all the time, so it's something you really need to know cold. The whole shebang builds right on top of this model. Moving on to Section 2, Transport, Addresses, and Ports. Now that we have the overarching map, let's zoom in on the exact mechanics of how data is packaged and delivered across the network. Okay, we're zooming in on layer 4, the transport layer, for the epic showdown between TCP and UDP. TCP is connection-oriented. It guarantees delivery using a 3-way handshake, SYN, SYNAC, and ACK. It's highly reliable, sure, but a bit slower because of all that overhead. UDP, on the flip side, makes absolutely zero guarantees. It's a connectionless fire-and-forget protocol. It is lightning fast, which is why we use it for video streaming and DNS, but packets can and will get lost. Why does this matter to us? Because attackers exploit these exact behaviors. They might use a TCP SYN flood to totally exhaust connection memory, or a UDP flood for a massive volumetric denial-of-service attack. Let's talk destinations. 4.3 billion, that is roughly the number of unique addresses available in the IPv4 format. Think of an IP address as your network's postal address. Made up of 4 8-bit octets, these IPs are split into public and private ranges. Public IPs are globally unique and visible to the whole internet. But private IPs, like that classic 192.168 network you probably have at home, those aren't visible online. They rely on your router to translate them. During network recon, knowing right off the bat if a target IP is public or private instantly tells you if it's directly reachable from the outside. But, just getting to the building isn't enough. You've got to get into the right room. That's where ports come in. And there are exactly 65,535 of them. Just picture these as virtual doors on an IP address. Servers are basically just sitting there listening on specific ports for someone to knock. Let's look at the hacker relevance of these virtual doors. If port 21 is open, that's FTP, which, crazy enough, often still allows anonymous logins with plain text credentials. Port 22 is SSH, an absolute prime target for brute force attacks. But the real alarm bell? Port 445, SMB. It turns out exposed SMB ports are infamous for enabling some truly devastating lateral movement attacks. We're talking legendary stuff here, like Eternal Blue and the WannaCry ransomware. When you review the default behaviors here in the source material, it becomes pretty obvious why memorizing them is basically a superpower. Admins might try to hide services on non-standard ports, security through obscurity, but knowing these defaults lets you easily identify services during your scans. Tools like Nmap are going to sniff them out regardless, for sure. All right, Section 3, Core Infrastructure, focusing on DNS and DHCP. Let's decode the actual communications infrastructure that makes navigating the internet possible without pulling our hair out. So this is the 6-step sequence of DNS, the internet's phone book. Without it, you'd literally be memorizing IP addresses for every single website. First, you type a URL into your browser. Second, your operating system checks its local memory cache. If it's not there, step 3, the query shoots over to your recursive resolver, which is usually your ISP. Step 4 is this crazy chain reaction querying root servers, then top-level domain servers, and finally the authoritative name server. Step 5, that server hands back the A record, which is the IPv4 address. And finally, step 6, your browser actually connects to that IP. Simple, right? Well, sort of. Now, similarly, DHCP is what automatically hands out those IP addresses to devices joining a network, so admins don't have to do it manually. It uses a 4-step sequence we call DORA: discover, offer, request, and acknowledge. But watch out, because there's a massive danger here. An attacker can set up a rogue DHCP server. If they manage to reply to your discover request first, they assign themselves as your default gateway. Just like that, all your traffic is flowing directly through the attacker in a classic man-in-the-middle setup. Yikes. As the guide showcases right here, attackers absolutely love to hijack these foundational sequences. Take DNS poisoning, for example. An attacker injects false records into a resolver's cache. So you type in the totally correct URL, but that poisoned cache redirects you to a malicious IP address controlled by the attacker. Next thing you know, they're stealing your credentials or dropping malware onto your system. Moving on to Section 4, subnets, firewalls, and attacks. Now that our infrastructure is completely mapped out, let's shift over to the active war zone of security defenses and offensive tactics. Okay, firewalls filter traffic based on rules. Stateless firewalls, they just check individual packet headers, making them super vulnerable to fragmentation attacks. Stateful firewalls actually track the connection state, which attackers can bypass by exploiting trusted connections. Next-gen firewalls use deep packet inspection, so hackers naturally try to hide in encrypted tunnels. And then web application firewalls, or WAFs, block malicious HTTP patterns, which attackers dodge using obfuscation. But actually, here is the absolutely crucial takeaway from the guide regarding firewalls: rule direction. Ingress rules block bad stuff from coming in, but egress rules, the ones controlling outbound traffic, are frequently just neglected by admins. And that, my friends, is exactly why reverse shells, where the victim's machine is tricked into calling out to the attacker, slip right through corporate firewalls. Let's run through a rapid-fire list of attacks tied back to our OSI model. Layer 2, data link, that is where ARP spoofing happens, leading straight to man-in-the-middle attacks. Layer 3, network, is prime real estate for IP spoofing. Layer 4, transport, is where those TCP SYN floods we talked about earlier occur to just totally exhaust server memory. Layer 5 is session hijacking, stealing your session tokens. And Layer 7, the application layer, is the absolute undisputed home of DNS poisoning and HTTP floods. The source guide specifically organizes all this into a quick reference table, and honestly, for very good reason. Interviewers absolutely love candidates who can rattle off this data perfectly. If you can instantly associate ARP spoofing with Layer 2 and SYN floods with Layer 4, you're proving that you don't just know the fancy buzzwords. You're proving you actually understand the mechanics of the battlefield. Which brings us nicely to our final section. Section 5, the ultimate interview question. We're bringing all these concepts together for the climax of our briefing. Okay, let's treat this like a high-stakes rehearsal. The interviewer leans in and asks, what happens exactly when you type google.com into a browser? Well, here is the exact fluid movement of that data. First, at 0 milliseconds, the DNS lookup translates the domain into an IP address. Second, at 50 milliseconds, the TCP three-way handshake establishes a reliable connection. Third, around 100 milliseconds, TLS negotiation happens to encrypt the data. Fourth, at 150 milliseconds, the actual HTTP request is finally sent over that secure tunnel. And finally, at 200 milliseconds, the server's response is rendered right there by your browser. Boom, nailed it. This capstone sequence is so critical that the source guide literally puts it under a massive pro tip banner. Aspiring professionals, seriously, take note. Being able to recite and truly understand the sequence from memory is the ultimate proof that you comprehend how all these disparate layers, protocols, and addresses actually work together in the real world. So, you now hold the tactical map. You know how the packets travel, how the handshakes work, and exactly where the vulnerabilities hide in plain sight. Remember, everything in cybersecurity travels through this network. So as you gear up and head into your very next cybersecurity lab or step into that big technical interview, I want to leave you with this final thought. Looking at the map, which layer will you exploit or defend first?